All right. In chemistry, we can generalize most reactions to fit into kind of one of five main types of chemical reactions that we come across. Those are listed here. We have synthesis reactions, decomposition reactions, combustion reactions, single replacement reactions, and double replacement reactions. So most of the reactions we'll see throughout this course they're going to fit into one of these five things: either synthesis, decomposition, combustion, single replacement, or double replacement. Now, the way we classify a reaction as one of these five types actually really depends on what happens in the chemical reaction equation. For things like combustion, you would think like, okay, well, I just look for when stuff is burning, but combustion is a little bit more specific than just, there's fire there. And sometimes our observations in the lab can actually mislead us into getting the wrong reaction type. So our surefire way to figure out what type of reaction is happening is to look at the chemical equation. Okay, we should be able to figure this stuff out also just based on the reactants. It helps if you also have the products listed as well. Makes it a little bit easier, but just with the reactants, you could be able to figure these ones out. So that way, if you say, I want to put this and this together and propose a reaction that happens, you can figure out what type of reaction is going to happen, and that can actually help you predict what products you're going to make. So we're going to start it off a little simpler. We're just going to start with what are the reactants and what kind of reaction type are we dealing with those reactants coming together. So let's kind of give an overview real fast of these five types. So synthesis reactions are a reaction where we put together stuff from simpler substances and we combine them into one thing. So there's a couple key things here. You can think of these simpler substances that we start with in our reactants as just pure elements. Okay, and specifically, we make one product out of this. One product. Okay, so in my general form down here, my A and my B would be just regular old elements right off the periodic table. Okay, and the substance that we produce and make is going to be here, our product here. We're going to shove all of those elements into one substance. Okay, so we're not going to have like this and this makes this and this. It's going to make one single chemical product. That's the easiest way to tell synthesis. Now, again, if you're dealing with just the reactants, it gets a little bit harder to tell, but based on the fact that we're putting together just regular elements, we should be able to combine them together into one compound. So our tip-off can be we're dealing with single elements at the beginning. Now, something to be careful of. You may remember from talking about covalent bonding that some substances would rather bond to themselves than be absolutely alone. So aside from some of our metals, nonmetals like zinc, Zn, is fine on its own. Let's see, magnesium is fine on its own. A lot of the metals are fine on their own. We can have just potassium, stuff like that. So those would be pure element forms of those reaction or those substances. So just Zn and just Mg, just K. But there are some elements that will pair up with themselves. So for instance, if we try to have just elemental hydrogen, H, what we find is that these guys don't actually like to be alone. They can covalently bond to themselves to give themselves that extra valence electron they need to become more stable. So rather than hanging around as just single H's and being kind of lonely and depressed, they can pair up with themselves and become H2, and they're a little more stable that way. So we don't really see hydrogen as just H, we see it as H2. The other elements that do this are oxygen, to make O2, fluorine to make F2, bromine to make Br2, iodine to make I2, nitrogen to make N2, and chlorine to make Cl2. Okay, so these 7 elements will pair up with themselves. We call these diatomic elements. They would rather be diatomic and be H2 or O2 rather than just H or O. All right, so these still count as elements. Okay, because they're not compounds of some other thing. It's not H and O together or H and Cl together. It's just H. Just happens to be that 2 of them is better than 1. Okay, so if we put together H2 and O2, that's a synthesis reaction. It's just 2 elements combining to make one new thing. Or if we were to put together hydrogen and iodine, H2 and O2 would also be a synthesis reaction, combining together to make one compound made out of hydrogen and iodine. Okay, so be wary of these 7 diatomic elements. They naturally come together as diatomic. They don't sit around as just single atoms. They don't sit around as monatomic. Okay. Other stuff, like again, zinc, magnesium, potassium, will just be on their own if it says elemental. It'll just be zinc or just be magnesium, just one atom of one thing. But these 7 guys will pair up with themselves. An easier way to remember them is by the funny sounding word Hofbrinkel. And that's kind of what this spells out. Hofbrinkel is Hofbrincl. This is why I wrote it in that order. Okay, so Hofbrinkel is the list of 7 diatomic elements that are always pairing up with themselves. You can also rearrange it into Brinkelhof. Sometimes people find that one funnier. Or you can also say 7-up. If you look on the right side of the periodic table, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine make kind of a 7 on the right side of the periodic table, the way they're arranged. And then hydrogen is up from that on the left side. So you can think 7 up. And it's like, you got the 7 things, and 6 of them are over on the right, making the shape of a 7. And then the 7th thing is up. It's hydrogen. So whatever way, just be careful of these diatomic elements. They are still just elemental. All right, what about decomposition reactions? Okay, in a decomposition reaction, we break a substance down into simpler substances, okay, sometimes to pure elements. And when we are predicting products, we are going to assume that it will always be down to pure elements. So I'm going to cross this out here. Substance is broken down into pure elements. I guess I don't need the 2 there either. There we go. All right, now again, don't forget, these guys count as pure elements. So if we are taking a compound made of a couple different elements, a compound, all right, something like this AB made of 2 different compounds, and making it go through a decomposition reaction, it's going to break down into just the elements that make it up. Okay, so if it's made of H and Cl and we break it down, it will turn into H2 and Cl2, not just H and Cl. Okay, now again, if it's not one of the 7 diatomics, like zinc or magnesium, then it will just show up as that thing. So putting together, say, magnesium chloride, okay, will break down into Mg as one element and Cl as an element. But Cl has to be a diatomic, so that's going to be Cl2. Okay, now, so let's be kind of careful of. I did not choose this 2 because the 2 is over here. This is for how the compound is made. So this would also work for KCl. Okay, so if I had potassium chloride decomposing and breaking down, it would turn into K, which is my element of potassium. Then I'd also get Cl, with the elemental form of Cl, but Cl is a diatomic. Cl2, not just Cl. Okay. Combustion is probably the easiest to identify if you have the products. If not, it's still pretty easy to pick out because it's very particular. In combustion, we have to have something made of C's and H's and maybe some O's react with some O2. Okay, we end up making carbon dioxide and water every time. The balancing is going to be different depending on how your reaction goes, but the products are still always going to be some number of CO2s and H2Os. So if you have the products CO2 and H2O, then that's a pretty dead giveaway, like, that's a combustion reaction. But if you're only dealing with the reactants, the other giveaway is I have C's and H's, maybe some O's, reacting with O2. That makes it a combustion reaction. Okay, so C's and H's, like CH4 plus O2 would be a combustion reaction, or C3H8 plus O2 would be a combustion reaction, or C6H12 12O6 plus O2 would be a combustion reaction. Anytime we have C's and H's, maybe some O's, reacting with oxygen, O2, the elemental form of oxygen, that's going to be a combustion reaction. And our products are always going to be carbon dioxide and water. Okay. In a single replacement reaction, we have an element that stays kind of by itself and switches its place in a compound and kind of kicks something else out. So usually this is a pure element plus an ionic compound, where the pure element kind of switches in and takes the spot of either the cation or the anion. Okay, so let's do an example for this one too. Let's say I've got yeah, let's do our MgCl2 again. And then let's say we are reacting it with sodium. No, let's do potassium. MgCl2 plus potassium. All right, so our magnesium chloride and our potassium are going to react. Note it doesn't matter the order that these are in. Like right now I have the element on the kind of second thing, but it could be K plus MgCl2, doesn't matter. Okay, but I have one pure element plus a compound. When this reaction happens, my K is going to come and take the spot of either the Mg or the Cl. Well, K tends to be positive as an ion, just like magnesium, so it's probably going to take magnesium's spot. Magnesium will get kicked out. It'll be hanging out on its own as a pure element. And then my potassium is going to go pair up with the other thing, K and Cl. Now be aware, this has to kind of follow making a good ionic compound, so our charges have to cancel. So I got lucky that one K and one Cl can kind of cancel out. Potassium has a positive one charge, chlorine has a negative one charge, but in other cases you have to be a little careful to make sure those cancel correctly. Okay, double replacement is kind of like a happier ending for single replacement. Instead of just kicking something out and it's like, get out of here, we end up switching partners. It's like a square dance. So we have two compounds, two usually ionic compounds that switch partners. So either the cation switch or the anion switch, doesn't really matter which one you pick, but they switch partners with each other. So let's say I had MgCl2 plus KF. Okay, well, in this setup here, Mg is my positive thing, and chlorine, Cl, is my negative thing. Potassium, K, is my positive thing. My fluorine, F, is my negative thing. So I'm going to either switch these guys, the positives, or I can switch these guys, the negatives. Okay, either way. Okay, I just have to make sure that my ionic compounds that come out on the other side actually cancel their charges correctly. Okay, so I'm going to switch my places of the cations just to kind of keep it simple. So instead, my K is going to be with my Cl, and my Mg is going to be with my F. Okay, well, now I just have to make sure that these make happy compounds. So my K has a positive charge, my chlorine has a negative charge. So positive and a negative should cancel out as is. So I don't need two Cl's just because I had two Cl's over here. I mean, I only have the two Cl's here to make a happy ionic compound. I don't need two Cl's to make potassium happy here. So my formula is fine as KCl, as is. For something like this, though, Mg has a positive 2 charge. Fluorine has a negative 1 charge. Okay, so this one negative charge is not going to be enough to satisfy this magnesium here. So I'm going to need 2 fluorines to cancel out that positive 2 charge with this negative 1 charge. Okay, just like how we had to have 2 Cl's for this Mg back here. Now we need 2 Fs. They both have a negative 1 charge. Okay, so these are the 5 main types of reactions. Okay, in synthesis, we have some pure elements come together to make one product. In decomposition, we have one single reactant break down into elements. Okay, so if you're trying to tell these apart just by the reactants, for synthesis, look for just elements in your reactants, only pure elements, no compounds. In decomposition, look for just one single compound that's going to break up. No, this plus something else. It's just something, and then your reaction arrow. In combustion, your reactants have to be some C's and H's reacting with O2. It has to be that way. Otherwise, it's not combustion. I don't care if it puts off a flame. I don't care if it burns like crazy. It's not technically a combustion reaction if it doesn't have C's and H's reacting with O2. Okay? A single replacement reaction is made of a compound and a single pure element. Okay? And I guess I should write that here. Okay, so we need an element and we need a compound in our reactants. Okay, where the element works its way in and kind of puts itself into the compound and kicks something else out in the process. It kind of wife swaps a little bit, but not really. And then in our double replacement, we have 2 compounds reacting together. Okay, typically 2 ionic compounds, where they switch either the cations or the anions. So we're looking for a reaction that has 2 compounds from the get-go. Now, one of these that's easy to get mixed up is combustion with single replacement. Since single replacement is an element and a compound together, I mean, combustion is too. We've got an element and a compound. But the way that the combustion reaction runs is more specific. Okay, so be careful of that. Combustion can look like a single replacement reaction, but if it's C's and H's reacting with O2, it is more specifically a combustion reaction.